permission to interrupt me because I'll probably go a bit too fast sometimes. But I might revoke this permission at any moment for the whole group or for certain individuals.
Fair enough.
Oh yeah, and I will quote some people in the room, and if I misrepresent you, please be angry. Okay, see if we can resolve it. So I'll start with Brett. I think it was 1999 you published the locality scandal in quantum mechanics. So let me just, let me just first say this part is largely divided in three parts. Yes, first I will talk about EPR and Bell states and how the quantum state of two electrons is usually represented and discussed in those contexts. I will talk about the helium atom because it's just a simple example of having two electrons in the inner shell of a helium atom, in the inner shell of an atom. And then I will talk about something called BMW entanglement. So it's a certain type of entanglement also for two electrons. So let's start with the EPR Bell states. And here I start with a paper from Fred from 1999, the locality scandal in quantum mechanics. So let me just start quoting it. So Fred starts by saying, well, here we have Bohm's 1951 version of EPR's Duncan experiment in terms of this spin half singlet state. What is this mathematical thing that represents that? So it's a proper state in a 2 by 2 dimensional tensor product over space. C2 tensor C2. So this is the space for the spin degrees of freedom of two electrons. And this is the typical state that is discussed in the context of EPR experiments where Alice measures one electron and Bob measures one electron. And then later Fred says, I should say F.A. Muller says, the state space of two spin 1/2 particles where in space, time and spin are all taken into account. Because here we've only talked about spin, and he says, well, shouldn't we also talk about the spatial degrees of freedom? So then we have a bigger Hilbert space, which has parts for spin and parts for space. Elements of this Hilbert space are the quadruples of two-particle wave functions, blah, blah, blah. Due to the exclusion principle, the anti-symmetric spin singlet state must be combined with a symmetric spatial state. Well, this is because if you go to this full two fermion state, you've learned that state has to be anti-symmetric, meaning that if you interchange the labels 1 and 2, you have to get the minus sign. And because this state is already anti-symmetric, you have to combine it with a symmetric spatial state to get a complete anti-symmetric state. Remember, you can interrupt. So the important part is down here. The solution of the free Schrödinger equation is just a product of this spatial state and the Bohm singlet, so the spatial and the spin part. Now let me paraphrase this a bit more simply. So, by the way, I'm omitting all normalization factors and coefficients, so don't bother about those. So, Miller first writes down the spin part of the Bohm singlet state. Only spin degrees of freedom are considered. Then he suggests combining it with the spatial state. And here, I gave a general symmetric state. I'm now giving an example where we have a wave packet on the left and a wave packet on the right. And then we arrive at this total state by taking the tensor product, which is just combining the two states. So I'm not sure if Fred intended it this way, but there's something weird going on here, because usually when we, in the context of EPR Bell experiments, we write down this state, we mean that we have one particle under control of Alice, who's, for example, on the left, so that's particle 1 here, and one particle controlled by Bob, say he's on the right, particle 2 here. So this would then mean particle 1 is on the left and particle 2 is on the right. If you look at this final state, you see particle 1, well, in one term it's connected to this wave packet on the left, but in this term it's connected to the wave packet to the right. So it seems if we represent the state in this way, then no longer we can say particle 1 is on the left, particle 2 is on the right. It seems to be both at both places or either place or whatever you want. So that's something a bit weird. Not sure if you intended this or.
Yeah, I intended it to be weird.
Okay, yeah, so that's giving an easy. So, but maybe so I want to clear up this confusion a bit. So maybe it's better to write for this first initial, like when discussing EP or flow experiment, not use labels 1 and 2, but use labels like L and R to be clear about, yes, we're talking about electron on the left and electron on the right, and not about like electron 1 and 2. So, but I wanna investigate. So then, how does this representation with the Hilbert space decomposed into left and right relate to like this representation with Hilbert space decomposed in 1 and 2, with them both being having like S-tests of being left and right. So to do that, I go to a bit simpler state. So here we see a term which says wave packet on the left, spin up, wave packet on the right, spin up, and here it's actually the same, only the labels 1 and 2 are interchanged. So this we would normally interpret as two electrons with spin up, one on the left and one on the right. So, and this is also a state that can be discussed in context of Bell experiments. For example, after Alice and Bob have measured their electrons and say they both found them to be spin up, then this is usually a way you can write it down. But we normally do not include spatial parts, and we write something like this, just electron spin up on the left and electron spin up on the right. How do we go from the one to the other? So here's one way you can do that. Pick a complete set of two orthogonal projectors, for example PL and PR. So just to emphasize, the L does not necessarily refer to the left wave packet, but say we divide the whole of space R3 into two subspaces. So one, let's say with the x coordinate less than 0, and one with the x coordinate greater than or equal to 0. And these projectors, they project to like the Hilbert subspace corresponding to those two spatial regions, and together, if you add them, you just get the unity operator. So once you have done that, apply PL tensor PR to this state, and you see because tied to the second term, you get 0 because you apply PL to the right wave packet that vanishes. So only the first term remains. Now we move to a smaller Hilbert state where the vector spaces are the eigenspaces of PL and PR, and change labels accordingly. So and I'll emphasize that this first Hilbert space is about wave projected on the left, and the second Hilbert space is projected on the right. And now we might omit the spatial part. So here we have still these wave packets, but we might say, well, we don't really care where exactly these wave packets have support. We only care that one is on the left and one is on the right, and we just throw away the spatial parts and spin part remains. So this is a way to go from like the full two-electron anti-symmetrized state to a state which is normally used in the literature to discuss EPR Bell experiments.
Sorry, Gijs, just for clarification, the tensor product, is that tensor product between H1 and H2?
Which one?
That, yeah.
Which one?
Yes.
Yes, this one is still
defined in terms of
Yeah, yeah,
H1
so
and H2.
confusing because it's like, yeah, these
Okay,
substrates.
thanks.
Yeah.
Well, and just to also clarify, so the next one down, that one, there you've got two Hilbert spaces, one of the left-hand
Yeah.
side states only, the other right-hand states.
Yeah. So, explicitly, we would have leftover space.
That's invisible, guys.
Yeah.
Do it on the left. Do it on the left of the board. No, so that it's not, you're not writing over your own
Yeah.
slide.
I would just. Okay. I was just putting it down again. Okay. Can you read this?
No. Why don't you write on the left
Oh,
so
sorry.
that you're not writing directly on top of your own slides?
There you go.
That's all right.
Sorry, I should listen.
Sorry.
So this is explicitly these silver spaces. Yeah, sorry if I move down again. Okay. More questions now, right now? Okay. But now let's, because I've of course been not really completely arbitrary by choosing BL and BR, having a wave packet on the left and a wave packet on the right. In general, this procedure will not always work because, for example, suppose we start with this state. Wave packet on the left, spin up, wave packet on the left, spin down, well, all the way around. Actually, this is about the same as the helium atom state. So this you can maybe interpret as having two particles with the same spatial properties, one with spin up, one with spin down. If we now apply this projector to BL, PR, we fail because applying this will annihilate the state against zero factor. So there's a solution for this. So instead of just going to the smaller Hilbert space, we take a direct sum of Hilbert spaces. So for both the left and the right Hilbert space, take the direct sum of like the zero particle electron Hilbert space, which is just only has the vacuum state, single particle, one, and two electron Hilbert space. And two things I forgot here. First, for the left one, I want to have like x less than 0 here and here. And for the right one, I want to have x greater than or equal to 0. Also, on the two particle state, you can of course take the antisymmetric sector because for two fermions, the state needs to be antisymmetric. And now, by appropriately combining the application of this first set of projectors we have, but also BL tensor BL and BR tensor BR procedure, I'm now kind of hand waving, but I think it works, always succeeds. So in this case, you would, in the case if you apply BL tensor BL, you would not get a 0 factor, you actually just get this thing in total. And then we just send that vector to the left Hilbert state. And then you end up with this state, saying like on the left we have singlet state, and on the right we have vector state. So, yeah, I've not completely been explicit here how this exactly works, so you have to, so I can try to explain a bit. If you apply this one, whatever you get out of that, you send to the subspace with one particle on the left and one particle on the right. You apply this projector, whatever you get, you send to the subspace with two particles on the left and 0 on the right. And you apply this and you send it to 0 particles on the left and 2 on the right. And if you can also get a superposition of having, for example, 2 particles on the left and 2 on the right, or any combination. And so I thought this can be generalized to n particles, will become a lot messier, but this can be done. Any questions? Okay. I'm not going to reach my hour. Okay, so let's go to the helium atom. So the helium atom is just a simple example of having an atom with, I suppose it's in the ground state with 2 electrons in the inner shell. Of course, 2 protons, 2 neutrons as well. Now I'm quoting Wikipedia about the Pauli exclusion principle. And then we read, the neutral helium atom has 2 bound electrons, both of which can occupy the lowest energy state, acquiring opposite spin. A spin is part of the quantum state, the 2 electrons are in different quantum states. Do not violate Pauli principle. Pauli principle says 2 electrons cannot be in the same quantum state. But this is just saying, well, it's satisfied by these 2 electrons because one is spin up and one is spin down. On the other hand, when we read Stephen's Stanford Encyclopedia entry, we find things like this. If the non-intrinsic state-dependent properties are identified with holomonetic or relational properties, which can be expressed in terms of physical magnitudes. I'm going to paraphrase it more simply in the next slide. Standardly associated with self-adjoint operators that can be defined for the objects, then it can be shown that 2 fermions in a joint endosomatic state have the same monetic properties and the same relational properties one to another. Consider, for example, 2 fermions in a spherically symmetric signet state, which is the case in the ground state of the helium atom. Fermions are not only indistinguishable in the above sense, but also possess exactly the same set of spatial temporal properties and relations. If you read this, it kind of suggests that the 2 electrons are not in different states, they're in the same state. And when I looked up this paper, I was so stupid, probably you know this joke, but I didn't know, to just type French redhead on Google. Maybe.
Yeah, you really don't want to do that.
You get a translation of redhead into French, who's for women and who for men. I get a lot of pictures of French redheads. So add the year and then you'll be fine. Yeah, so this is just saying a bit, or like say the conflict or the issue a bit simpler. So if you just express only the spin part of the ground state of the 2 electrons in the helium atom, like this. And one way we can say we have now 2 electrons in the same state, because if you, the procedure to now get the state of electron 1 and electron 2 is to take a partial trace. And if we do that, we get for both electron 1 and electron 2 this same state, which has like a term for spin up and one spin down. But we've also seen sources which say, well, no, we have 2 electrons in different states. One with the state spin up and one with the state spin down. So this seems like in direct conflict with each other, but I think they're both correct in a sense. It just depends on how you decompose the 2 electron Hilbert space into 2 Hilbert spaces for the individual electrons. But I am going to argue that actually I think this second way is the more natural way to go. So if you take a partial trace, you're really taking these labels 1 and 2 quite literally, like this is talking about the 1 electron and 2 is about the other electron. This is something that Adam Colton has called factorism. And Adam calls himself an anti-factorist. And I think I largely agree with them that it's kind of misleading to really focus on like the labels 1 and 2 here, and I'm going to tell you now why. So, because when we write down this state, we're kind of neglecting all the other electrons in the universe. And I want to talk about that. To do that, I'm going to make it a bit simpler. Suppose the universe only consists of 5 helium atoms. Suppose non-relativistic quantum mechanics is perfectly exact and everything. So there are 5 helium atoms located at let's say, 5 distinct wave packets located at A, B, C, D, and E. Now, if you then write down, so they're all in the ground state. If you then write down the full 10 electron anti-symmetrized state, we get this. So I've written down the first term, which says, well, we have electron at A, having spin up, but also spin down, and at B, spin up, spin down, C, blah, blah, blah. And then we have to anti-symmetrize it, and you do this 10 factorial minus 1, because you need to have all the possible ways to swap the labels. So if we again, as like we did here, you're going to ask like, oh, what is the state of individual electrons? If you just take partial traces of electron 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then your result will be that all 10 electrons will be in the same state, will be represented by the same density operator, which is a mixture of being at A having spin up, being at A having spin down. So these are 10 terms total. But this is not what we usually want to do, I think. Because usually what we say, oh, we have here atom number A, and now we're going to talk about the 2 electrons belonging to atom A. So how do we do that? Because here we see, well, every electron is actually not located at a single atom, and here we see it's not the product state, so we cannot just like consider only Hilbert space 1, Hilbert space 2, and then say, oh, we're going to talk about those 2 electrons, because that will never give us the 2 electrons belonging to atom A. But what can we do is the same we did before, but then with a bit more factors. So you can apply these 10, this tensor product of these 10 projectors, where we have 2 times. So again, we have like a set of 2 projectors which are orthogonal, which project 2 orthogonal subspaces, and together they are the unity operator. If we apply this big projector, then only 2 terms remain of these many terms. And again, we can go to these smaller Hilbert spaces. So I've already, and then incorporate this into the labels, which I've already done here. So we get, we get more than 2 terms, but important point is that you can write the state like this. This is 2 electron. This is a 2 electron state for the 2 electrons in the A atom in the ground state. And then we have here many other terms with wave packets at B, C, D, and E. And then we can just say, well, I'm going to throw away description of these other electrons. Just going to stick to this first part, because now we see what the product state. And then we see we have a signet state of the 2 electrons of atom A. But why stop there? It's quite arbitrary, I think, to just having chosen this A and this A perpendicular, or say the other subspace. Yeah, we can again apply the procedure with P projected to spin up and P projected to spin down. And then we get this thing, and then we can just say, okay, I have a Hilbert space corresponding to the electron in atom A with spin up. Well, surprise, it's in spin up state. And I have a Hilbert space corresponding to electron A spin down, and of course electrons in the spin down state. And I've now done this in 2 steps. First, applying these projectors with spatial properties, and then projectors with spin properties. But we could as well just immediately here have chosen P, A, and also project and spin up. And all the others project, all the 9 other projectors project to the orthogonal subspace. And then we would immediately go from this first state to a state saying, okay, we have 1 electron in atom A and it has spin up. So that's why I think it's quite arbitrary to focus on, say, oh, we have some helium atom with this state, and because to get to this state, you already have to distinguish these two electrons from all the other electrons in the universe. You have already used. You have to use a property of the pair of electrons to be even able to write this down. And I think that's quite arbitrary. You could also already say, oh, I'm also selecting, projecting them to spin up, and then then I end up with a single electron having spin up in the inner shell. Maybe some intermediate questions, comments? Yeah.
Can you just say a little bit more about, you said it's quite arbitrary. I'm not quite sure I see what the problem is. I mean, this goes back in a way to what you said about what Adam said about factorization. Is the problem the factorization, is the problem the assignment of labels? Because if it's the assignment of labels, you just, you adopt what Schrödinger said. You chuck in a bunch of labels and you permute them around. The labels lose their significance.
Yeah.
They're just there to get the maths going in a way. You need something to hook this onto.
Yeah.
Is that your worry, or is it something else when you say this seems arbitrary?
So what I mean to say is, usually many discussions also about developing identity of like two electrons in a two electron state. You just start by saying, okay, we have this state, as if, like I say, as if there's nothing to say about how did I even, how can I even talk about these two electrons without talking about all the other electrons in the universe. So I've tried to make explicit here,
Okay.
in a universe with 10 electrons,
Right.
you have to do some work to get from what you might call like the total or fundamental state of all the electrons in the universe to the state of only two of them. And I'm saying if the thing you need to do to make explicit what you're maybe implicitly doing here, you can do the same thing with this state.
Right.
And then, so if you're going to say, I have two electrons of electron A in a single state, I say, well, then you might as well also say, I have one electron with spin up and one electron with spin down,
Okay.
because you're doing the same thing, essentially.
Right. Okay, thank you.
Yeah.
Yeah, but I mean, similar question really. I mean, here, I mean, you are projecting onto PA. I mean, it's still the tensor product of H1, H2 to H10.
Yeah.
So, you're selecting out not just electrons at location A, but electrons 1 and 2 at location A.
Yes.
Now, why don't you take say that operator plus PA per PA, and so on,
Yeah, so
with all possible pairs of electrons
Yeah, so it's,
at A.
so I've been arbitrary as well in just putting the A's at the start and the rest.
Yes.
But I think, so I could have just as well put these A's somewhere else. And what the result would be is that the labels here will be permuted. So for example, if I would do the last two, if I put the A's at the end, then this would just interchange this factor with all the rest. So you would just, but I don't think that, I mean, once we're at this stage, we know that we mean with this label like, oh yeah, we've projected onto A. So I don't, you can switch these. I mean, also you've read my paper, the corporate grammar paper. I'm quite easy about like swapping if you have tensor like up L, down R, I can write down R, up L. I mean the same thing. So what I'm saying, once you have written down these labels and you know that these labels correspond to this operation of projecting, then it doesn't really matter anymore, I think, what the order of the tensor product is. So, of course, there's a lot of symmetry in this state, right? So you only need, in this case, if you know the first term, you know them all, in a sense. Because it's just the anti-symmetrization of the first term. But that's why we only need to pick out one term. And a way to do this is applying this projector. If we would put the ace on another, sorry, we're not picking out one term, we're picking out multiple terms, but if we would have put these a's on another location, we would just get essentially the same, but only commutative labels. So maybe
I'll let you
go
go
on.
on.
You can go on.
I'm still somewhat puzzled.
Yeah. Do it.
Yeah, could you get me a bit back on track maybe? So why to include these A states, or in the simple case at the beginning, this right and left space? So I understand.
Wait, go back in the slides or this slide?
Yeah, maybe just the first state that you wrote down with R and L. So I'm just wondering why we need. So I understand that we usually talk about Alice and Bob in different locations. Where is this really in the? What is the goal of this? Where is this really in the formula?
Well,
because when you want to show Bell inequalities, for example.
Yeah, so it's
can just use up and down.
because of this confusion that actually I think arises from example Fred's paper. And you see sometimes people saying, well, we have an EPR Bell experiment and the state is in the singlet state, which is fine because it's anti-symmetric and the Fermi Schupik anti-symmetric, and then I'm like, oh, that's confusing because we can also have up in the Bell setting. We can have Alice has spin up and Bob has spin up. And that's not anti-symmetric at face value, but it is fine. And then the story is, oh, but wait, if we go to the full Hilbert space, including the space degrees of freedom, that has to be definitely anti-symmetric. So I was wondering, like, so how do these exactly relate? How do they clear up this confusion about singlet state being anti-symmetric and the full state, including the spatial part?
Right, full state of the electrons include the spatial part. And
Yeah.
that
So although
changes the whole approach to Bell inequality.
so I think all literature is fine because you can just translate these kind of states, which are usually written down. You can just translate them back to full two electron states if you want, but it makes it more complicated to do. Like if you do now write down the operator to measure the left particle, you have to have a symmetric operator on Hilbert space 1 and Hilbert space 2. So it's more complicated. So this is just way simpler to do, and I think it's completely fine to do it in that way. Yeah, and also so now that I've talked about these helium atoms, so I should also say that here are also there is some story about how this supposedly fundamental two electron state relates to the other electrons in the universe. So you already need to use a property of these two electrons together to even be able to talk about them as, and not about all the other electrons. So.
Can I just ask something about? So can you carry on to the next slide? Yeah. I mean you've chosen a basis there, so
Yeah.
up and down and Z. So.
Yeah.
But if that was really the state, if either electron was in a pure state of X or of Z spin,
Yeah.
then it would have to be in a superposition of spinning Y and X.
Yeah, so
So
there are
I've
multiple-
lost the symmetry of the state there, because that,
so I've broken the symmetry by choosing,
yeah,
in my projectors I've chosen Z. I could have chosen X as well and I would get the same. So this is just an example that there are multiple ways. So if you have the singlet state, you can say, you might say I have one electron Z up and one electron Z down. But you might also say I have one electron X up and one electron X down. And in general there are multiple ways. Also I think for this 10 electron state, we've started with saying, okay, we're gonna choose like projecting on the support of, which includes this A wave packet, and we're projecting on the rest of the space. We could have chosen very weird subspaces, with different, probably, maybe you could say, oh, I have one electron being in superposition at A and at B. So I think it's maybe quite pragmatic about this, but I think it's quite arbitrary how you decompose these 10 electrons into 10 individual electrons. And there might be multiple ways.
isn't that a reason not to go as far as this step? Because this step then breaks the symmetry and implies that,
Yeah, but I think that
you know, it's a bit like taking the ignorance interpretation of the mixture. So if you take the maximally mixed state up and down next, and you've obtained that from the Bell state, then you can't interpret that as a proper mixture, because if you wrote it, if it was a proper mixture, then it would be the same in every basis.
Yeah.
So I mean, that's what's worrying me here.
Yeah, but so I cannot completely be convincing now, because I don't have this explicit in my head now. But I think even, I mean, you do agree that going from this to this is fine, right? If we have a state like this, then talk about the 2 electrons of atom A. Right?
Okay.
That's what we do all the time. I mean, if I talk about the electrons in this piece of furniture, then I could include the electrons of that piece of furniture as well. We have like a big antisymmetric state. To go to the electrons of this piece of furniture, we can project onto this space. And then, I mean, if we cannot do that, we would have to like discuss all the electrons of the universe all the time. We don't do that. We pick out electrons according to where they are, essentially, most of the time, or with spin properties. But I think in doing that, we do the same thing already, because I think you can choose different projectors, and then you have a story like, oh, we don't have 2 electrons belong to atom A, but we have 2 electrons which are in superposition between electron A and electron B. Like I said, I would have to think this through and try to make it explicit. So maybe I'm very convincing right now. But I think you're essentially doing the same thing going from here to here as you are going from going to here. Of course, this is kind of, these Hilbert spaces are one-dimensional, so not much freedom left. You've actually, the labels completely now kind of specify the state already, because you know that it's located at A, and you know that it's spin up. There's not really much to state. I mean, you cannot have like here spin down anymore, because I have projected to the spin up property, and I've shrunk my Hilbert space to.
But spin up in the Z direction, that's what I don't understand, because if the electron was determinately in a pure state up in Z.
Well, it's about what is the electron. So when you go from 10 electrons to 1 electron, there are multiple ways to do it. So one way to do it, you end up with 1 electron with spin Z up at atom A. You can choose other projectors, you get a spin X up in atom A. So I admit it's arbitrary, and there are multiple ways you can get from 10 electrons to 1 electron. So I'm probably just saying there's no preferred way to get at this single electron. Okay, we have 20 minutes left. So let's go to I got to my final part and then plenty of time for questions. So this is about GMW entanglement. I've now just copied the slide from a talk by Adam Colton in 2013. So GMW is for Girardi, Marinetti, well, let's not discuss both. He says fermionic state is GMW entangled if and only if it's not the anti-symmetrization of the separable state. So what's the motivation of even talking about something like GMW entanglement? It's because, for example, look at, sorry. No, let's look at this stage. So you might, if you follow some quantum mechanics text, you might be inclined to say that this is an entangled state because it's not a product state. So you might say, oh, well, you see here electrons 1 and 2 are entangled. On the other hand, we usually interpret this as electron 1, having an electron on the left having spin up and having an electron on the right having spin up. And we saw with this procedure we can write it down like this, and then we would say, no, they're not entangled, because this is a product state. But the question is, how do we just have like a general rule for full, let's for example, two electron states anti-symmetrized? How can you have a general rule to say, are they like entangled in the proper way? Like, so that would mean this is not entangled, but for example, the singlet state is entangled. One. Instead of just saying it has to be, is it a product state or not, because that doesn't work obviously, because we want this state to be not entangled in that way. We want this state to be entangled in that way. So GMW entanglement is one attempt to do this, and just defined as being it's entangled if it's not the anti-symmetrization of a separable state. So then Adam gave some nice results. The thing I want to focus on is this last thing. An assembly state is GMW entangled if and only if it violates a Bell inequality for some symmetric variables. I'm just reading variables as observables here. I'm not sure if I'm right in doing that. Makes it easier for now. I think it's just wrong. Which I will now show. So let's start with this product state. L plus wave packet on the left, wave packet on the right. Spin up. Wave packet on the left, wave same spatial state, spin up. So this is clearly a product state. We anti-symmetrize it. And we get this, we just get, because the spatial part is the same, so here I've also switched around with the tensor product factors. So here we see the spatial part is the same, and then we get singlet state for states. And so this is an anti-symmetrization of a separable state, of a product state. So this should count as, so it is the anti-symmetrization of separable state, so it is not GMW entangled, according to the definition. Okay. Not GMW. However, the expectation values of these symmetric observables, what we see here is, this is just like the simple product of spin in direction A and B and symmetrized, combined with projectors on the left and on the right, which you could interpret as finding one particle on the left and finding one particle on the right. you can just work this out and you will see that you will violate Bell inequality for using the standard Bell angles for alpha and delta. So these are symmetric observables. So according to this statement, it should be GW entangled, but it's not. So this is a counterexample. One way to make this a bit more insightful, maybe, is that this state can be expressed like this, like having a term with left-left, having a term right-right, and then having this is just a standard Bohm singlet state. So suppose you start with first seeing if you have indeed one particle on the left and one particle on the right. You will have a 50% probability that you indeed find one on the left and one on the right. And there will be like 25% that you will find two on the left and two on the right. In the case you find them both at the same location, you just discard them. But in the case you find one on the left and one on the right, you see, and you haven't measured the spin yet, see we just end up with the Bohm singlet, and we all know we can violate Bell inequality with that. For example, you can just think of preparing a million of these states, of pairs in this state, send a million particles to Alice, send a million particles to Bob. Be sure to, you can like wait 1 second in between so that they know which pairs belong to each other. And all the pairs where Alice finds two particles or Bob finds two particles, they throw away. So they end up with approximately half a million particles, which are all EPR singlet state, and they can theory violate Bell inequality with that. So I threw this into a talk where Adam was present, and he was quite surprised. Unfortunately, I haven't been in contact with him. What he thinks about it now. I did look on the internet, because I thought I was original with this. Then I found in the physics community, this was actually, I didn't put it in the slide, but if you read this paper, you found exactly this example. And they say, oh yeah, GW entanglement is one of the attempts to characterize proper entanglement for two fermions, and it's for this reason not the right way. And there have been other attempts, and this paper actually proposes something else, and they say, well, we just haven't found the correct way to characterize entanglement for two atoms already. And this was already in 2009, so we should be in contact with the physics community a bit more maybe, because Adam's paper was long after this. Yeah, so that was actually the third part. So this is it. I would like to thank some people and things. So first, cheese of last night, because it gave me enough calories.
It was good cheese.
I had 2 of these to finish this talk. So thanks to the knee replacement. And I would like to thank David Chalmers, because he has to leave really early in the morning or late last night, how we interpret it. And I could use his room to finish this talk with looking at the water and the hospital. That was nice. So that's it.
Okay, well, thank you very much, Gijs. Okay, 1 minute to
1 minute.
formulate the question.
Out.
Because I just breathe in, breathe out. Just when you thought you understood entanglement. Okay, hands please. James, number 1. Guido, number 2. Simon, number 3. Okay, well that's for the first round. James, go ahead.
Yeah, I suppose I don't understand what that upshot is. Like, are we supposed to take away from this the idea that we should believe that in the first orbital of the helium atom, every atom, every atom apart from hydrogen, there's an electron that's determinately spin up in a particular direction? Because if that was true, then that would imply empirical predictions that
No,
are
so
falsified, right?
I would not say that there would be any empirical things that would be really surprising. So the opposite, I think, is that in one way of going from many electrons to one, you could end up with saying, yeah, we have one electron in the inner shell having spin Z up. So I think what I'm probably,
I mean, if we said that, then we should attribute the pure state spin up in Z to that electron, and then...
No, so the normal rules of like composite systems and individual systems do not apply here. Yeah, because of this whole story. So you were saying, so suppose I'm saying, well, you could say that we have one electron that spin up in the inner shell of the electron. You say, yeah, what would be the empirical consequence?
Well, if you had a large ensemble of such atoms, presumably you could say the same thing about all of them, and then you could measure the electrons and find that they're in a... So if they were really in the pure state, one of them was up in X and one of them down in X, then you get different statistics for an ensemble of measurements than if they were in the entangled state. Up plus down, minus up down, minus down up. Yeah.
Well, I think it's not the case if you're really careful about saying what you mean by saying, like, this is the way I ended up saying we have an electron with Z spin up in the shell. Because if you're saying, how would we measure the spin of, how would we measure the spin of the two, or one of the electrons? So if you want to, for example, if you want to measure the spin of that electron, using this story, you would, I mean, how you're going to find that electron? Well, in this procedure, I've said, oh, you find it by projecting onto the spin up subspace. So then, of course, kind of trivially, you wouldn't even have to measure it. You would say, well, of course, it's set spin up. Because, like I said, it's a one-dimensional Hilbert space you end up with. So yeah, once you have chosen this procedure to go to this single electron, you already know it is that spin up. And if you would try to write down like observable measuring the spin of that electron, well, it's in a one-dimensional Hilbert space, so it has one eigenstate and one eigenvalue. And you're definitely going to find that spin up. But this is kind of by definition. So if you want to do what you say, like I'm going to just measure the spin of those electrons, then I would want to know how do you write down the operators? And my answer, I think, would be, well, it would be kind of trivial because when you write it down, you immediately see, well, and if you want to measure like the Z spin of them both, well, you know also what you're going to find. You're going to find one up and one down. If you're going to measure the X spin, let's see. You're going to measure the X spin while you have said that one is Z spin up and Z spin down. Yeah, we'll have to. At least I know what you cannot do is say I'm going to measure Yeah, so that's a good point. I have to see where it exactly breaks down when you're trying to say I'm going to measure the X spin of the left one and the X spin of the right one. Because if you measure the X spin of both those inner shell electrons, it needs to be that they're also always going to be opposite. Well, if you look at this, like you, I think you were suggesting, there's a probability that they will both be X spin up or both be X spin down.
Yeah.
So, but I think somewhere along the road you will find that you just cannot write down these operators.
So does anything different happen for 2 electrons in EPR experiment? I mean, if it's determinately true that in the helium atom, one is up and one is down, does that not go for 2 electrons in a
No,
EPR apparatus?
And so I don't want to say that this. I mean, you might. I mean, from if you want, you can say I have electron 1 and electron 2, and they're both have up and both down. So I'm not saying this is like a wrong way of decomposing the electrons. I'm just saying maybe that this is maybe the more natural way, because even to get that, you're already using properties to distinguish the 2 electrons from the rest of the electrons in the universe. So you might just as well use the properties of spin to separate these two electrons. But I'm not saying this is wrong. I mean, if you want to say that every electron of the universe is in the same state, well, yeah.
But sorry, I'm just really confused, because once I say the last line, then I lose the correlation between the spins in the other direction.
Yeah, so that's the same point we just discussed.
Yeah.
So
I'm just making the same point over again.
yeah, so I have to think that through. But as I said, I think somewhere along the road you will see that you have problems like even defining. You just really, yeah. But I have to think about it. I think.
Guido?
About the GMW stuff, so I guess the physical motivation for the definition originally is, well, if we've got symmetrization or anti-symmetrization, that's a cheap way of getting entanglement, but surely when we are doing the Bell experiments, that's not cheap entanglement, it's really something going on there, let's try and characterize that. And then mathematically, okay, I mean, this is nice results too. Presumably there is proof of that result. And now what you're pointing out is, well, that result may be true, but physically it's not interesting, because what's happening physically is we are not working with the GMW. We are not working with that non-GMW entangled state. We are measuring that there's a particle here and a particle there. So essentially we are collapsing that state in order to get an interesting entangled state.
No, we don't have to.
And that violates the Bell inequalities.
Well, that was just kind
There's
of.
post-selection.
No, that was just to make it kind of insightful that how could you violate the Bell inequality with this state. But actually, you don't really need to talk about post-selection or anything. If you really just apply this symmetric observable to this state, you will see that you just statistics violate the Bell inequality. And just like first measuring the position and then the spin, and then post-selecting is just one, you could say one explicit implementation of Fermi's measurement. But you could make measurement devices which just do this all net. But I mean, that's just one way of. So this kind of suggests that you need to post-select or something, but I don't really want to put much weight on that, because it's just really this observable violates statistics violate Bell inequality with this state. And I think
Okay,
it's just
so-
a contradiction. So I think this is not only like uninteresting, I think it is wrong. And
Okay.
it has to do with, so I'm still working on like where in the proof does it go wrong, and I think it has to do with that they just don't consider, they already consider cases where you have one on the left and one on the right, and neglect cases where you can have both on the left and both on the right. So they're
Okay,
already,
so they are post-selecting implicitly. Yes, in a sense.
Yeah, you could say, or pre-selecting that they don't even.
Yeah, or pre-selecting.
Yeah.
Okay, Simon?
Well, yeah, I've got a really short question, but it relates to this. Remind us, what do you mean by symmetric variables? Why talk of
Yeah,
variables?
so this is, I have to admit, this is Adam's slide. I didn't look up how exactly he defined this, but I think, so I hope I'm right. I think this should count for symmetric observed fields as well.
Right, so symmetric.
That's how I just interpret it.
And my other question is just, when did you talk to Adam about this?
In Köln, the GWP conference.
Ja.
Was that-
But I
was
sent
that
him an
3 months
email.
ago?
Deutsche Gesellschaft für Wissenschaftsphilosophie.
It was a few
Oh,
months
okay,
ago.
a few
He was
months
there.
ago, right.
Yeah.
I mean, I've been speaking to Adam about this, and
Okay.
I do think it's important to find out who's right about this, actually.
Yeah.
It's certainly important to me.
So I think I sent him an email that probably asked like way too many questions in one
Right,
email.
right,
So,
I mean, right, so, I mean, Adam claims to have proof. He hasn't published it, as I understand.
I think he has put it in one of his like preprints. Yeah.
Oh, okay, good,
But as I said, there's also just these physics papers which just say
yeah.
mention GMW entanglement and say it's not
Very right.
sufficient. So that I'm not original. Because I mean, I thought I was, but this is already
Yeah.
found out by others. So.
No, but this is an interesting sort of discovery,
Yeah,
because with us sort of philosophers of physics, and also James wrote this paper with Thomas, etc. Finally, we know now exactly what entanglement is. This is a GRW entanglement, but well, apparently there's a counter example. So,
yeah,
but apparently physicists
If
knew
it's
about
right.
it. Knew about it some time ago. That's also what you discovered.
Yeah.
Anyone else? If not, then we stick to the program. Something about a lunch. Well, I have listed the various options at the back of the conference document. One thing, if you don't want to go into the heath, you can go in this building downstairs and then walk in that direction. At the end, turn right, and there is a place to buy lunch. You can also go outside to food court, where there is a larger variety of choices, and that's also nice.
Let's thank
Yeah.
Yeah, here.